Hi. Well, I sure had a lot of fun recording lecture 14A about continuous dynamical systems with differential equations and talking about vector fields and solution curves in vector fields. Here in lecture 14B, we're going to talk about discrete dynamical systems. In the second part of the lecture, initially I'll just review determinants and tell you a little bit more about them. But then we'll move on to linear difference equations in two dimensions, especially ones related to geometric examples and their solutions. I'm thinking in particular about dilations and rotations. We also could think about reflections, but I didn't feel like I had time to do that with this particular lecture. So I'm excited about this as well, more connections between these two subjects. Let's jump ahead to the linear algebra content. Let's start by reviewing determinants from lecture 13B. What's the 2x2 case? In other words, what's the determinant of a 2x2 matrix? If the matrix has entries A, B, C, D, the determinant is A times D minus B times C. Multiply the entries on the main diagonal. The main diagonal goes from upper left to lower right. And then subtract the product of the numbers on what you could call the non-main diagonal or off diagonal, B times C. That's the 2x2 case. What about the 3x3 case? I did mention the formula that I'm going to show you is related to something called a cofactor expansion, also called a Laplace expansion. And I probably will talk about that a little bit more to some degree. Not in this lecture though. You're just trusting me that this is a good idea, okay? We'll talk about why with regard to the properties. The determinant of a 3x3 matrix like this, where the entries are A, B, C, D, E, F, G, H, I. E is not the number E, I is not the imaginary unit. These are arbitrary real numbers. Is this, which simplifies to that. Okay, now that's not a formula to memorize so much as a formula you can use if you want, but it's really more of a procedure, and I will tell you the procedure here, this cofactor expansion. I did mention it in 13B as well. Across the first row, notice the A, the B, and the C are the entries of the first row, though with a plus sign here, a minus sign here, and a plus sign there. These signs alternate plus, minus, plus when you go across the first row. The quantities in the parentheses, EI minus FH, DI minus FG, DH minus EG, are determinants of 2x2 submatrices of this 3x3 matrix. For the first one, you take this number A in the first entry, first row and first column. Imagine crossing off that first row and first column, and you're left with a 2x2 matrix. The determinant of that matrix is E times I minus F times H. For the next term, with the negative B out in front, B is in the first row, second column. Cross out that first row and that second column. You're left with a 2x2 submatrix whose determinant is D times I minus F times G, which is what you see there. But don't forget the minus sign there. And then plus sign plus C. C is in the first row, third column. Cross out the first row and third column. You're left with the 2x2 submatrix whose determinant is D times H minus E times G. Exactly what you see there. And then you can distribute it through if you like. But it's the procedure that's easier to remember. Properties that I talked about in 13B that work for any square matrix of any dimension n by n. A matrix where the number of rows is the same as the number of columns is called a square matrix because it looks like a square. These properties hold even though I'm not telling you the general formula or the general procedure. Okay? It's not too hard to learn it. It's kind of just not of interest to us so much. You could learn it. But these properties are really what's more important. First one is the most important. A square matrix A is invertible. It's got an inverse matrix, A inverse, that we can find with the row operations like we talked about recently, if and only if the determinant is non-zero. It's invertible if and only if the determinant of A is non-zero. This is also called, a bit more terminology, non-singular. In that case, when A is invertible, when its determinant is non-zero. In the case where A is not invertible, the determinant will be zero. And that's called singular. So it's a little strange. Invertibility goes with non-singular. Non-invertibility goes with singular. Why this extra terminology? Well, it's kind of related to the fact that a determinant being 0, in the case of non-invertibility, is a rare event, a singular event, almost like a singularity, or rare thing. Whereas invertibility, with the determinant being non-zero, is more common, you might say. Non-singular, non-rare, not a singularity. Okay? Something to watch out for. I probably will use that term from time to time. Another fact, given two square matrices A and B of the same dimension so that you can actually multiply them, determinant of A times B is the product of the determinant of A with the determinant of B. Determinant of this matrix product is the product of these two numbers. Determinant of A and determinant of B are numbers. I'm multiplying them here. Okay, I didn't put the dot in there. That's understood. This actually extends to product of finitely many such matrices. I got the determinant of A1 times A2, etc. through AN. That's the determinant of A1 times the determinant of A2, the 2 there, times dot 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 times determinant of AN. The determinant of the product is the product of the determinants. This is true whether the matrices are invertible or not. Though if even one of them is non-invertible, then the determinant is going to be 0. The whole determinant of the entire product will be 0, and the entire product will be non-invertible in that case when its determinant is 0. If even one of those matrices is 0, that will happen. Furthermore, if IN is the n by n identity matrix, which we talked about before, its determinant is 1. Its determinant is the product of the numbers on the main diagonal, which are all 1s. And actually, we're going to see that for any such diagonal matrix, whether it's the identity matrix or not, the determinant is also the product of the numbers along the main diagonal. That's part of why it's called the main diagonal. There's also something called triangular matrices that's related to that. And if A is invertible, then the determinant of A inverse is the reciprocal of the determinant of A. This is a division of numbers. This is a raising to a power of a number. When A is invertible, so we're not dividing by 0 there. Okay? These are the most useful properties in general. There are some other properties I want to mention. Also useful when necessary. That comes now. For an n by n square matrix, the following statements are true. A, the determinant, this is referring to what I just mentioned, the determinant of a triangular matrix is the product of the entries on the main diagonal. What is a triangular matrix? A triangular matrix either has all zeros below the main diagonal, in which case it's also called upper triangular. So here's the main diagonal from upper left to lower right. If you've got all zeros in the entries below that main diagonal and to the left of it, then that's called upper triangular, and that is an example of a triangular matrix. Or zeros above the main diagonal. You've got the main diagonal, you got all zeros above and to the right of it. That's also triangular, sometimes called lower triangular. The triangles in upper triangular and lower triangular refer to where the possibly non-zero numbers are. Or it could be both, zeros below and zeros above. In that case, it's also called a diagonal matrix, like I mentioned a minute or two ago. In any one of these cases, the determinant is the product of the entries in the main diagonal. Again, that's part of the reason it's called a main diagonal. It's extra important. More properties. These properties are related to row operations. And we'll probably use them in the next lecture, 15b, to do some calculations. Interchanging two rows of the matrix that we're given multiplies the determinant by -1. If I swap two rows, I get a new matrix, a different one than what I started with. The determinant of the new matrix is -1 times the determinant of the old. You swap two rows. Of course, if you swap them again, you multiply by -1 again. -1 squared is +1. You get back to the original determinant. Even if you swap two rows and then swap two different rows, you've done row swapping twice, so the determinant of the new matrix after two row swaps is the same as the determinant of the original matrix, even though the matrices themselves are different. Multiplying a row by a constant multiple, multiplying a row by a constant, multiply the determinant by that same constant. So if I got a matrix, a square matrix, I multiply, say, the third row by 7, I get a new matrix. That new matrix has a determinant that's 7 times the determinant of the original matrix. Performing row replacements, perhaps somewhat surprisingly, row replacement operations, the most common row operation we do, leave the determinant unchanged. That's actually going to provide a calculation method for the determinant. When we got a matrix to start with, if we go to row echelon form or reduced row echelon form, even row echelon form will get an upper triangular matrix, and the determinant will be the numbers in the product of the numbers in the main diagonal. Now, if even one of them is 0, then the determinant will be 0. More facts. If V is this vector AC and B is this vector B, or W is this vector BD, then the parallelogram spanned by V and W has area equal to the absolute value of the determinant of the 2 by 2 matrix whose columns are V and W. In other words, the absolute value of the determinant of this matrix. That's why I did A, C, and BD, so that this matrix would be A, B, C, D. And that, of course, simplifies to the absolute value of AD minus BC. And because there's absolute value signs there, I could switch it around, though most people don't typically do that. You could if you wanted to. What is this parallelogram spanned by V and W? Sorry about the vacuuming thing. I should say something. Okay, it'll be done soon, hopefully. The parallelogram spanned by V and W is the set of all vectors that are linear combinations of V and W where the weights are both between 0 and 1, including the endpoint 0 and 1 of those intervals. What is this? Well, we typically think of it as the set of all points whose position vectors are in that form. So if V looks like this, and well, let's make W go down this way. We want the set of all points that can be formed by linear combinations of V and W where the weights are between 0 and 1. A set of all points whose position vectors. And that is going to turn out to be this parallelogram right there. That's going to be the parallelogram spanned by those two vectors. Now, that's not the same meaning of the word span as when I've used the word span before, though it's a similar meaning. In general, the span of two vectors is the set of all linear combinations of them where the weights can be any real number. But when I specifically say parallelogram spanned, then I want the weights to be between 0 and 1. So I actually get an actual finite parallelogram of interest. The area of that parallelogram is this quantity. Okay? It's an interesting little exercise to see if you can verify that. You can with a pretty nice picture, actually. Another fact, if S is a subset of the plane, that's not the empty set. That's notation for the empty set there. S is non-empty, it's got at least one element. Oh, this is the empty set. It's the set with nothing in it, which is a set, actually. If this is a nice set, S itself, with a well-defined positive area, what would it mean to have a well-defined positive area? It's related to integration. That you can define the area. And if T, from R2 to R2, right over there, is a linear transformation with matrix A, then the image of S under T, which is defined by this equation, It's the set of all outputs of T as the input ranges over the set S. S itself could be some sort of blob, for example. You know, S could be some sort of blob of points sitting in the plane. That could be S. What are the set of all points that the points in here get mapped to under T? The set of all outputs, T of X, as X ranges over the set S. It's going to be a subset of the plane, and it has an area equal to the absolute value of the determinant of A times the area of the original set, assuming that area is well defined. Based on the previous fact, that might make some sense, though you need to believe the previous fact. Where does this come from? You can verify it, so to speak, with multivariable calculus, with double integrals. It's related to change of coordinates and Jacobian matrices if you've ever done that, but we won't get into that detail. Okay? It will be helpful for us to remember that, though, as we now start to consider examples of difference equations here. Okay, this is the fun part of the lecture, I think. Difference equations defined by linear transformations in the plane. First of all, given any function, linear or not, I didn't make it a boldface. I could have, but I'm thinking of it more as a mapping, not as a vector field as we talked about in lecture 14a. We can define the corresponding difference equation like this. Vector x sub n, and I'm using boldface, lowercase x, like I mentioned in lecture A where I was using boldface, uppercase y. I'm using this for difference equations. Equals f of x n minus 1. Actually, based on this scheme here, n can't be 0. N is 1, 2, 3. If I wrote it as x n plus 1 equals f of x n, which really means the same thing, then n would start at 0. But here I'm starting with this notation with n equal to 1. But when n equals 1, we are talking about x0 in that case, 1 minus 1 being 0. Where xn is this vector whose components are non-boldface xn and non-boldface lowercase yn. This is a difference equation. We can keep using this equation over and over again. We can iterate this function. In Mathematica, we could use nest list to do it. We'll show you some Mathematica at the end of this lecture. For any given initial condition, initial point x0, whose components are this x0 and y0, in R2, going back and forth between thinking of elements of R2 as points and thinking of elements of R2 as vectors, this generates a sequence of points, vectors, x0, x1, x2, x3, etc. x1 is going to be f of x0. x2 is going to be f of x1. I take the previous output and it now becomes the input. x3 will be f of x2. I take the previous output and it now becomes the input, etc. I started with an initial vector, x0. This set of points, this sequence, is often called the orbit of x0 under f. Why? Does it orbit around the sun or something? Well, no, it's just kind of a fun term to use. It's moving around the plane like the orbit of something could do around the sun, but it's not necessarily saying it's an accurate model of that. If f happens to be a linear transformation with standard matrix capital A, the orbit can be found by repeated multiplication of the matrix times itself. Think about each step here. Okay? xn, by definition, is t of xn minus 1. But t has matrix capital A, meaning t of xn minus 1 is the same as a times xn minus 1. But wait a minute, xn minus 1 is the same as t of xn minus 2. That's a function applied to an input. This is a matrix times a vector. This is a matrix times a vector. The vector happening to be the output of t at xn minus 2. But yeah, the formula for t can be applied again to say t of xn minus 2 is a times xn minus 2. And then essentially the associative property says you can regroup the parentheses there to have a times a in parentheses times xn minus 2, which is the same as a squared times xn minus 2. Which is the same as a squared times t of xn minus 3, etc. And at the very end, you're going to get down to that. Keep following this pattern. Dot, dot, dot means some skip steps. Lots of skip steps there, and is big. In other words, this is a solution of the difference equation. A to the n power times x0. Why? So xn is a to the n power times x0. This solves the difference equation. Left-hand side equals right-hand side for the difference equation. This thing with a t instead of an f. Because the left-hand side is just xn. The right-hand side is t of xn minus 1. That's a times a to the n minus 1 x0, which is a times a to the n minus 1 times x0, which is a to the n times x0. I'm thinking about this equation, this difference equation right there. Hardest time with markers. This difference equation right here with a t instead of an f, where t of x is a times x. Left-hand side is just xn itself. Right-hand side is t of xn minus 1, which simplifies to the left-hand side. Xn, this thing, is the left-hand side. Right-hand side simplifies to the same thing. Assuming that, for example, the associative property works there. And it does. I've proved that, but it does. This is very analogous to what we did back in lectures 1 and 2 when we were talking about scalar difference equation. Say yn was k times yn minus 1. And we wrote the solution as yn equals y0 times k to the n power. Very analogous, right? Got an x0 vector in place of a y0, a to the n in place of a k to the n. That's a vector, this is a scalar. That's a matrix, this is a scalar. But you see the analogy? The vector does need to be on the right side of the matrix if I'm thinking about vectors as column vectors here. Very similar thing. Connections. But that begs a question. How do you raise a matrix to a power? Well, you do keep multiplying the matrix by itself, but how do you do that? Is that very easy to do? Do you just raise the entries of the matrix to that same power? The answer is no, you do not, except in some very special cases, like diagonal matrices, for example. I should also mention here that when n is 0, a square matrix to the 0 power is defined to be the identity matrix, analogous to a non-zero number to the 0 power being equal to 1. The non-zero matrix to the 0 power is defined to be the identity matrix. Okay, that's a definition, and that makes the initial condition work as well, because you get a to the 0 times x0, which is I times x0, which is x0 itself. The orbit of points is sometimes relatively easy to understand, like with dilations, rotations, and reflections. Sometimes it's harder to understand for combinations of these geometric effects and maybe some other geometric effects. Combinations are the combinations going to be compositions? Possibly. We'll get to that eventually. All right, so now we're looking at examples. We're going to look at 3 main examples, what I call pure dilation, a mixed dilation, and a rotation. What is a pure dilation? When I say the word dilation, it could be an expansion or a compression. Visually, it could expand points away from the origin, make sets bigger when you consider their images, or compress points toward the origin, make sets smaller when you consider their images. Dilation includes both expansion and compression. It's one word to include them both. Not necessarily like dilating your eyes, don't take it too literally. We're talking about 2 dimensions here to make it easier, though I could generalize this to higher dimensions. It's a linear transformation from R2 to itself whose standard matrix takes this form. Capital A is a diagonal matrix, both upper triangular and lower triangular. There are zeros below the main diagonal and zeros above the main diagonal. I am taking the number on the main diagonal to be positive because it keeps things simpler. It's an expansion if A is bigger than 1, and a compression if A is between 0 and 1. If A equals 1, then it's really the identity matrix, which doesn't do anything to points. It just leaves them where they are. Neither an expansion nor compression in that case when A is 1. Let's relate this to determinants and areas. The determinant of this matrix is A times A minus 0 times 0, A squared. Determinant equals A squared. So T, or the action of T, you might say, multiplies areas by a factor of A squared. It's not that T itself does the multiplication. It's that the action of T on a given set with a given area gives you an image whose area is A squared times the area of the original set. By that determinant fact. And A squared is positive, so you don't have to worry about absolute value signs. Which makes me realize the next slide actually has a typo. Well, actually it doesn't because the numbers will be positive. What are the orbits of points? What happens when you iterate the function t, when you keep multiplying by capital A, when you raise A to the nth power, all this stuff still holds. This is general thinking here. We're just talking about an example here. Find the solutions. Once again, typo. I should not start at 0 with this notation here. Well, from the previous slide, what's on the board? We need to find A to the nth power. What's A squared? This matrix times itself. Think about it with dot products. 2 by 2 times 2 by 2 is going to be a 2 by 2. The first row, first column entry is going to be the dot product of the first row with the first column here. A times A plus 0 times 0 is A squared. Entry in the first row, second column, is going to be the dot product of the first row of the matrix on the left with the second column of the matrix on the right. A times 0 plus 0 times A is 0. Second row, first column, dot product of this vector with this vector, 0 times A plus A times 0 is 0. Second row, second column, dot product of second row with second column here. 0 times 0 plus A times A is A squared. I guess with the diagonal matrix, I could square the entries, including the zeros if I want to think of it that way. But it's actually best to just emphasize that they're 0. A cubed is going to be similar, and you can cube the entries on the diagonal of this diagonal matrix. And in general, A to the nth power is this. Which means I can now take this expression and figure out what it equals. The solution of the generic IVP for a generic initial condition is this. I'll not move. There we go. xn is a to the n times x0. There's a to the n. There's x0. If you actually do the multiplication, you get this vector. And if you want, you can factor out the a to the n. Careful, this is a matrix times this vector, capital A to the n power times this vector, giving you a vector. This is a number times the vector, a scalar multiple of the vector, which also is a vector, and it's the same vector in this case. It's so important to keep track of what's a number, what's a vector, what's a matrix. That really helps you to work things out and avoid confusion. So ultimately what matters here is a to the nth power. If a is bigger than 1, like 2 for example, you get 2 to the n times x0, the point's going to move further and further away from the origin. Whereas if a is 1/2, you get 1/2 to the n times x0, that's going to move closer and closer to the origin as you keep iterating. A mixed dilation, that should be a mixed dilation, which could be an expansion and or compression in two different directions. In the standard directions, horizontal and vertical is what I mean by standard directions, along the axes. It could expand in both directions, or it could compress in both directions, or it could expand in the horizontal direction and compress in the vertical direction. Mixed dilation is a linear transformation whose standard matrix takes this form. Now it's still a diagonal matrix, but now I'm allowing the lower right entry to be different than the upper left entry. Previous example was a multiple of the identity matrix. This, if A and B are different, is not a multiple of the identity matrix. Think about how this expands and or compresses. Pause the video, think about it. You back now? If A is bigger than 1, it's going to expand in the horizontal direction. If it's between 0 and 1, it's going to compress in the horizontal direction. If B is bigger than 1, it expands in the vertical direction. And if B is between 0 and 1, it compresses in the vertical direction. And you can have combinations of those things. The determinant is equal to A times B. So the action of T multiplies areas by a factor of A times B, which is positive, because I'm assuming A and B are both positive. What are the orbits? Find the solution like before. So just like before, we need to find a to the n power. And we still can raise the entries on the main diagonal to those same powers and leave the other numbers as zeros. That still works in this setting. It doesn't work in general. You can even try examples to see that it doesn't work in general. So a to the n is this. And that does allow us to solve the generic IVP. Xn equals that, equals a to the n times x0, which is this product, which you can multiply out, which we can expand out as a linear combination. Could have done that right from the start, I guess. And if I want to, 1, 0, and 0, 1 are the standard unit vectors. I could call them I hat and j hat, or, as I've talked about also recently, you could call them E1 and E2, boldface. And hey, that's a linear combination. Linear combination, I really emphasized that in lecture A. There's reason. The solution space, as I talked about in lecture A, is going to be the span of functions of the form a to the n times I hat and b to the n times j hat. And those would be vector valued functions, not of t as it was in lecture A, but of n here in lecture B. The solution space will be the span of those two functions of n. And those are going to be linearly independent functions. The solution space is going to be some sort of two-dimensional space as an abstract vector space. How about rotations? This is our last slide, but I want to show you a little Mathematica too. Rotation about the origin in two dimensions is a linear transformation whose matrix takes this very special form. You ready? That one right there. First column cos theta sine theta, second column negative sine theta cos theta for some real number theta. This is if theta is positive, this is a counterclockwise rotation by theta radians, say if theta is in radians, which you usually want it to be. Counterclockwise rotation when theta is positive, it's really a clockwise rotation if theta were negative. Note that the determinant of this is 1. Why? Because it's cos squared theta really plus sine squared theta, because the two minus signs cancel, which is 1, always, no matter what theta is. T preserves areas. Should make intuitive sense. Rotations preserve areas. They're rigid. What are the orbits? I guess they're going to rotate. Do all the things we did before. And here, so I got to find a squared, for example, matrix A times itself. You're going to get this, if you check that with dot products. That doesn't look so nice, but hey, there are double angle formulas, double angle identities. Cos squared theta minus sine squared theta always equals cos 2 theta. Always, no matter what theta is. 2 cos theta sine theta always equals sine 2 theta. And I've got a negative sign there, so I get a negative sign there. Double angle formulas or double angle identities. Huh, and that makes sense. A is a counterclockwise rotation, say by theta. I do it once, the angle is theta. If I do it twice, it's another theta. 2 theta is the total angle. I get a new rotation, really, is the net effect of 2 theta. It turns out that a to the n is a rotation by n times theta. And the solution of the generic IDP, you can double check, can be written this way. And hey, we have another linear combination here of these two functions of n. Those are once again going to be linearly independent functions that span the solution space in this example. And that will ultimately mean, since there's 2 of them, that the solution space somehow is 2-dimensional. Analogous to R2 in some way that I'm not saying at the moment. That is the last slide. Let's show you a little Mathematica too. For sake of time, I don't want to really explain this. Let's see. Let me delete the output. Ruin the surprise. This would be a pure dilation. A is 2. And R solves the difference equation. As a vector, it'd be 2 to the n x0 for the first component and 2 to the n y0 for the second component. You could factor out the 2 to the n, that's the a to the n. You could also do it in terms of, well, here's how it affects one initial condition when you apply t1s. Here is a to the nth power in matrix form. Here's what happens when I iterate the function. I keep multiplying by 2 each time. And then here is a graph showing you visually what's going on. As n increases, the point is moving away. It keeps going twice as far from the origin after each iteration. The next example is a compression, or excuse me, a mixed dilation. It's expanding in the x direction and contracting in the y direction with a given initial condition that I pick just off the y-axis. The solution graph looks like that. And here's a rotation. This one is by 30 degrees. And now this point gets rotated by 30 degrees, so it takes 12 iterations to get back where you started. It's a periodic function. Okay? Lots of really cool stuff, I think. I hope you stick with me and see more cool stuff related to this.